All right, so in Unit 3B, we're going to be putting numbers in perspective. So we're going to talk about scientific notation. Scientific notation is a format in which a number is expressed as a number between 1 and 10. So what you're doing is you're putting it times 10 to whatever power, how many times you had to move it. For example, they use these in very large numbers and very small numbers. If you had 6,700,000,000 written out like that with the 8 zeros. In scientific notation, you would have to move the decimal, which is at the end, the far right, and we would move it 1, 2, 3, 4, 5, 6, 7, 8, 9. So you want to move it to there's only one significant figure in the ones place there. So the way you would write it is 6.7 times 10 to the 9th, because you had to move that decimal 9 places to the left. Now, if you had a very small number here, you would still have to move that decimal where it's behind that significant figure 2. So I would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So that would be 2.0 times 10 to the negative 15, because I had to move that decimal to the right. So it would be negative. And the negative just means they're small numbers, so it tells you which direction to move it. And see how this exponent is positive, and it told you that you were moving to the left, so it'd make a larger number. Given meaning to numbers. Perspective through estimation. An order of magnitude estimate specifies a broad range of values, usually with 1 or 2 powers of 10, such as in the 10,000s or in the millions. Okay, so order of magnitude of ice cream spending is the total annual ice cream spending in the United States measured in thousands of dollars, millions of dollars, or billions of dollars. So what you want to do is you want to, which unit makes more sense when you're using it reasonably. All right, so we're going to guess that the average person has something like 50 servings of ice cream per year. That's almost an ice cream once a week. So when we're talking about the spending, you got 50 servings per person per year times $1 per serving. So it's $1. Then you multiply it by how many people are in the United States. So then we're going to multiply it by how many people, which this is scientific notation. You would have to take the decimal after the 3 and move it 8 afterwards to see it in standard form. So then you get 50 times 1, and then you get 1.5 times 10 to the 10th power, which is, when you think about that 10, if I moved it 10 over, it would be approximately $15 billion per year on that one. All right, so here they would give you a chart, and they tell you information about the energy or the joules, and they put it in scientific notation. Look down here where they have the U.S. annual energy consumption, and then they have the world annual energy consumption. Okay, so those two are in scientific notation. So let's do an example where we use the U.S. versus world energy consumption. Compare the U.S. population to the world population and the U.S. energy consumption to the world energy consumption. What does this tell you about the energy uses of by Americans? All right, the world population about 7 billion. So if we were to write that, it'd be 7 times 10 to the 9th in scientific notation. U.S. population is about 300 million. So then we would have to move it over there, and it would be 3 times 10 to the 8th in scientific notation. So you want the U.S. divided by the world population, because that's what we're comparing. Remember, you have your first one that they compare with. That always goes on top. Compare U.S. to the world. So U.S. is on top, divided by the world population. What happens is, if you remember your exponent rules, when you have the same base, you subtract the exponents. So 8 minus 9 would be negative 1. And then these two numbers, since there are in front of the 10 base, it would be 3 divided by 7. So 3 divided by 7 times 10 to the negative 1, that would give you 0.43, and then you'd move it over, so it'd be 0.0143. I will include a video on how to put in scientific notation, change scientific notation in the graphing calculator. All right, the other part of it is U.S. versus world energy consumption. The U.S. population is only about 4% of the world's population, but as shown in that table 2 slides back, table 3.1, the United States uses about 1 over 5.7, or about 18% of the world's energy. That is, Americans use more than 4 times as much energy per person as the world average. Perspective through scaling. So we're going to look at some maps. Okay? Verbally, if you looked at this, 1 centimeter equals 1 kilometer that is on this map. Graphically, you look at it like this, and at the bottom you could see this is a centimeter, and that equals 1 kilometer. If you were to measure that, that would be 2 kilometers, which would be 2 centimeters. As a ratio, 1 centimeter equals 1 kilometer means that the scale ratio is 1 to 100,000. Let's try an example using this. Earth and Sun. The distance from the Earth to the Sun is about 150 million kilometers. The diameter of the Sun is 1.4 million kilometers, and the equatorial diameter of the Earth is about 12,760 kilometers. Put these numbers in perspective by using a scale model of the solar system with a 1 to 10 billion scale. Okay? If we were going to scale the Earth to Sun distance, you would do the actual distance divided by 10 because that's a 10 to the 10th power, because that's a billions scale. So we would take this, because it said 150 million, and we would need to move them up to put the decimal in front of the 5 behind the 1. So the actual distance is 1.5 times 10 to the 8th, but we want to put it on the 1 to 10 billion scale, so we have to divide it by 10 to the 10th. And notice there's nothing written in front of that. That's understood to be 1 times 10 to the 10th in scientific notation. So when you look at this, it would be this divided by 1, which is 1.5. Then we do our exponents because these bases are the same. 8 minus 10 is a negative 2. Then we would multiply it times the 1,000 meters in 1 kilometer, because they wanted to convert it to meters. So you multiply it across. Now then what would you do here is when you multiply same bases, remember in your exponential properties, that would be negative 2 plus 3, so that would give me 1, so it would be 1.5 times 10 to the 1, and if I moved it from the left over to the right, that would give me 15 meters. Note that in the last step we converted the distance from kilometers to meters because it's easier to understand 15 meters than 0.015 kilometers. We find the scaled Sun and Earth diameter similarly, this time converting the units to centimeters and millimeters respectively. So the scale of the Sun's diameter, actual Sun diameter, is going to be divided by 10 to the 10th because we're still doing that scale that they asked for. So it would be 1.4 times 10 to the 6th kilometers divided by 10 to the 10th. Again, same basis, so you would subtract. 6 minus 10 is giving me the negative 4. This is understood to be 1 times 10 to the 10th, so I just bring down my 1.4. We're going to convert kilometers into centimeters, so it's 10 to the 5th, so it comes out to be 14 centimeters. Again, it would be the negative 4 plus the 5. That would be 10 to the 1, which means I would move that decimal place over once, and it's 14 centimeters. The scale of the Earth's diameter would be the actual Earth diameter divided by the scale that they want, the 1 to 1 billion. So it's 1.276 times 10 to the 4th. Again, remember at the bottom, this is 1 times 10 to the 10th power. So 1.275 divided by 1 is 6, not 5. And then if I subtract, 4 minus 10 is a negative 6. Now we're taking kilometers and we're going to convert it to millimeters. So it would be 10 to the 6th using your conversion chart on an earlier PowerPoint. And if you'll notice here, Negative 6 and positive 6 cancel out, and that would be 10 to the 0, which, if you remember your properties, 10 to the 0 actually equals 1 and not 0, so it would stay 1.276 millimeters. The model sun is 14 centimeters in diameter, is roughly the shape of a grapefruit. The model Earth is about 1.3 millimeters in diameter, which is about the size of a ballpoint on a pen, and the distance between them is 15 meters. So we've taken these huge numbers and tried to put it in perspective if you were going to put it in a model and scale it down. What is $1 billion? All right. One way to put 1 billion in perspective is to ask a question like, how many people can you employ with 1 billion per year? Let's suppose that employees receive a fairly high average salary of $100,000, and that it costs the business an additional $100,000 per year in overhead for each employee. Costs for office space, computer services, health insurance, and other benefits. The total cost of an employee is therefore $200,000 because they get a salary of $100,000, and then you have to pay this per employee also. So $200,000 is the total cost, and 1 billion would allow the business to hire how many? So you would take the 1 billion, divide it by the 200,000 per employee, write it in scientific notation. So we would take the 1 billion and we would put it in scientific notation, which would be 10 to the 9th. And then we would take the 200,000 per employee and put it in scientific notation, which, moving the decimal from the right, you would go over 5 spaces. So it would be $2 times 10 to the 5th. When you divide this out, you get 5 times 10 to the 3rd. If you would move that over, that ends up being $1 billion per year could support a workforce of 5,000 employees. Another way to put 1 billion in perspective, also point out how different numbers can be, even when they sound similar, like million, billion, and trillion. Suppose you have a sports star and earn a salary of 1 million per year. How long would it take you to earn $1 billion? We simply divide 1 billion by your salary of 1 million per year. So you would take the 1 billion divided by 1 million per year, put it in scientific notation, and you've got 10 to the 9th divided by 10 to the 6th, so you would subtract those. So you would get 10 to the 3rd, so it would take you 1,000 years. Even at a salary of 1 million per year, earning $1 billion would take 1,000 years. That's how you would write it out.